Hello everyone, this is the fifth and sixth lecture combined in a single video for our course EP1027 Maxwell Equations and Electromagnetic Waves. This week there was a class on Wednesday, but I wasn't able to put up a video for that. So today I'm going to cover the material worth of two lectures, today's lecture and Wednesday's lecture. Okay, so agenda is a bit long, as you can guess, because it covers two lectures. I'll talk about electrostatics. This will be a mixture of a review of what you've already learned in middle school or high school perhaps, and in your freshman year when you start using vector calculus to rewrite these equations which you've already learned in middle school or high school. So I'll start with the very basic, which is Coulomb force law, the first law to be written on electrostatics, static electricity. Then I'll speak a word on the system of units, which is conventional for this course. And then I'll talk about a little bit about maybe one slide on the nature of electrical charge, because I think not much discussion, not much light has been shed on the nature of electrical charge itself when you learn about it in high school. Then I'll define a quantity, a vector quantity, which is known as the electric field strength vector, or just electric field vector. And we will formulate or set up electrodynamics in terms of the electric field vector. Okay, so this is an important quantity which we will define in this class. And then we will say, as you know, for every vector field, there are two key derivatives which capture all the information about the vector, which are the divergence and the curl. So the divergence of this electric field vector will lead us to something which is known as Gauss law. You can think of it as a consequence of simple charge conservation, which measures the divergence of the electric field. There is a differential version, and which you will learn now, and of course there is the integral version. I believe you are already familiar with from high school. And then the curl will turn out to be zero. The electric field strength, at least for the static cases which we are discussing today, it will turn out that the curl vanishes. That leads to us to the conservative nature of the electrostatic field, because the curl vanishes, and as you know from the theorem we covered in the last class, that it leads to the existence of a scalar potential. So we will switch language from the electric field to the scalar potential because it's a scalar. It's much more convenient to handle. We don't have to be especially cautious about adding scalar quantities, we will rewrite Gauss law and everything in terms of the scalar potential, which will lead to a certain very important equation in electrostatic, which forms a cornerstone, something which is known as Poisson equation. Okay, after the French physicist mathematician Poisson, and then another Frenchman, Laplace, who worked out things for the simpler cases or special case of Poisson equation when for regions which are outside sources, outside electrical charges. Okay, so these will constitute the boundary value problem in electrostatics. Okay, solving the potential of which obeys these equations with certain boundary conditions. Okay, that is what constitutes the boundary value problem in electrostatics. And as you can imagine, the people spend a whole century solving these equations in various different coordinate systems, rectilinear or Cartesian, also curvilinear coordinate systems. However, all that we will not discuss in this course, because that requires a course, maybe a fractal course or two fractal courses on its own. These are second order elliptic partial differential equations, and a lot of effort has been spent in solving these analytically, also solving these numerically, which is the current way to deal with these equations. However, we won't have time to cover solving this, but we will set up the equation and we will see what kind of boundary conditions we need to solve these equations. Okay, and then based on these we will also see that certain results follow about the electrostatic field, which is known as Earnshaw's theorem, mean value theorem, and uniqueness theorems. The last two may be a bit more mathematical, which deals with the nature of the potential and whether the solution to this equation is unique given the boundary condition. Existence is not the fact that solution exists is one good thing. The next thing you test about a solution given a differential equation is whether the solution is unique. So we will look at that. And then Earnshaw's theorem, most of you I think are familiar from this in high school a little bit. The fact that the electrostatic fields electrostatic forces cannot hold the system of charges in equilibrium. This also will follow from the properties of these equations. So that will be most of general electrostatics, with charges present in general in vacuum. And then we will talk about electrostatics when we have media or matter. So before we go do that, we will review a little bit of electric dipole, which is kind of necessary before we talk about the effect of electric fields inside matter. So I will define what a point dipole is, or ideal dipole is, and what is the important thing to notice is what is the potential of a dipole. It will turn out that a dipole, instead of unlike the point charge, will have an inverse square potential. Remember, a point charge has the inverse 1 over x potential, 1 over r potential. Dipole will turn out to have 1 over r square. I will not work out the electric field from the potential. You can take the gradient and you should be able to find out what is the electric field. And the reason, as I said, we study this is because when you have electric fields in matter, which we will call dielectrics, matter, it will get polarized. That is, matter will develop electric dipole moments. Okay, so the way to think about this is think of matter as made up of small neutral molecules. Now, these neutral molecules, when you subject them to an external electric field, the center of positive charge and center of negative charges in a molecule, they will separate. The center of negative charges will shift toward the electric field in the direction, against the electric field, and the center of positive charges will be pulled in the direction of the electric field. Now, since the charges will separate, the center of charges will not overlap, each molecule will develop a dipole moment in the direction of the electric field, usually. It turns out in many cases it is not. We will cover that case as well. Usually it is, so molecules, the constituents of matter, develop a dipole moment, so they behave like tiny dipoles, and their combined effect can be thought of as as a continuum, as a lump which has a varying dipole moment density throughout the lump. And then this, we can use the physics of electric dipoles to learn about electric fields in matter, because now that we've established that they are small dipoles, it's a continuum of dipoles, we will see that it makes more sense to define something which is known as the electric field vector, which captures more information than the electric field. And then we'll study a special case. In order to get more mileage, we will study a special case which is known as linear dielectrics. In fact, we will talk about linear isotropic dielectrics, for which these get related in a way that you can actually solve the equations. So we will also set up boundary value problems for the linear dielectrics or linear isotropic dielectrics. And then a very important thing, which is the energy stored in electromagnetic electric fields in vacuum and matter. So this is important because this tells you that the electric field is a physical concept. It's not just some holy smoke or some ether or some spirit-like entity. It has energy, and I will also, later in the course, we will see it also has momentum. In fact, things can collide with it and exchange energy and momentum with it. By things, I mean charged objects and currents. They can collide with the electric fields and exchange matter and energy. So these are physical objects which play a great role. We will see what is the energy expression for the energy density in an electric field. How much is the energy packed inside per unit volume. And finally, we'll talk about conductors, which are another category of matter. As I said, matter can be classified into either dielectrics or conductors. Conductors, unlike dielectrics, do not develop a dipole moment because the molecules get completely ripped apart, or the atoms get ripped apart and they're stripped of their electrons. So what matter is inside, it is a bunch of free positive and negative charges. So when you apply an electric field, these free positive and negative charges, which are present in equal amount, will get pushed farther, as far as away as possible. And because it is so the approximation we will be making, conductors will have an infinite supply of positive and negative charges. So if you so this will lead to certain interesting consequences, which we'll discuss when we get to conductors. So the reference for this lecture, this set of lectures is Griffith's textbook, chapters 2 and 4. Chapter 3 I've omitted because chapter 3 is all about solving Laplace equation. Of course, Griffiths is not the best book to study this. Griffiths does have a lot of the basics. I think it's still, you can write an entire book on solving the Poisson or Laplace equation that we will not cover in this course. Okay, so chapter 2 and 4. These are the main references. So let's start with something which most of you are familiar from maybe middle school, which is the Coulomb law. Before we set up Coulomb law, we will talk about a few observations which led to the Coulomb law. Observation 1 was that constituents of matter, or elementary constituents of matter, such as protons and electrons, they appear in nature to be exerting forces on each other due to a particular property which is known as electric charge. So the fundamental observation is that constituents of matter have a property which is known as electric charge, which causes a certain kind of force. Let's call it electric force. This was observed by the Greeks when you have, when you rub one material against another, that friction causes transfer of electrons from one to the other. And because electrons have electric charge, the two materials which are being rubbed and get charge opposite, and then they attract each other, or there is some kind of spark. So the static electricity is generated. To explain this phenomena, we attribute certain property to constituents of matter, or particles, elementary constituents of matter, which are known as electric charge. Second observation is that the charges can be of two types, and which will determine the direction of the force. And we usually call them positive or negative. It is not necessary to call them positive or negative. You can call type A charge and type B, type A and A bar, something like that, complement. And this is the fact that charges come in two types or signs is only true for electrodynamics. For example, in gravity, this is not the case. When mass can only come in only one type, there is no negative mass. Okay. Similarly, if you look at the strong nuclear force, charges are called color charges, and they can be three different colors, and they're negative counterparts. So red, blue, green, and anti-red, anti-blue, and anti-green, for example. So it is not canonical that it is not something which very natural why there should be only two different types or two opposite types of charges. Nonetheless, this is an observation. And observation 3, of course, this is the famous observation which was given by Coulomb, is that the force falls off inverse square of the separation distance between the two charges. If we have 2 point charges and they're being attracted or pulled by this electric force, the force is actually inversely proportional to the square of the separation distance, and the force is central. By which I mean is that the force is along the line joining the two charges. Okay, so those kind of forces in which you have the source and you have the test or the effect, those two, if the force is along the line joining those two, then you call that force a central force. And most of you have learned about this in classical mechanics, and there's a famous problem called the central force problem, which you solved. So if you combine all three observations, this is what you get. So you have two charges, 1 and 2, with charge q1 and charge q2 respectively, and they're located at the x1 vector and x2 vector position vector respectively. What Coulomb's law tells you that, okay, the force on charge 1 due to charge 2 is proportional to how strong q2 is charged, second particle is charged, and of course it is also proportional to how strong q1 is, or how strong the first particle is charged. And it's of course proportional to the inverse of square, and it is along the distance which is separating, along the line joining at 1 and 2. Okay, this is combined in this equation. The proportionality constant is lambda e. These are all proportional. So we will have some interesting comments to make about this. It turns out you could have easily taken it to be 1, but the weird units which are prevalent nowadays, it's not 1, it's some weird number. We will see that. So this is kind of written in a nicer manner if we can make it a cube here, and then this unit vector becomes a normal vector. So this is the form we will use mostly. X over x is cubed, x over mod x cubed. So if I'm calling this x1 minus x2 x, this is x divided by x is cubed. And then you can replace, to get this force on the second particle, you replace every 1 by 2. So F2 will be Q2, Q1, which is the same, X2 minus X1 mod, which is the same, and then X2 minus X1, which is minus of this. So F2 is minus of F1. And so the electric force on two particles are equal in magnitude, but they're opposite in direction. Now, this observation has led a lot of cheap textbook authors to sort of make the comment that these are action-reaction pairs. The force on the first charge and force on the second charge, they're action-reaction pairs. Okay, that is farthest from the truth. Now, action-reaction pairs, it will turn out when we do electrodynamics and we include magnetic force and everything, there's a very easy way to show that these cannot be action-reaction pairs. In fact, this equation will not even hold true. So these are field forces, and they're taking place at two particles which are separated by some distance. So Newton's third law, which says that for every force there's an equal and opposite force, is only true for contact forces, right? Not for field forces, which takes place at a particular distance of separation. So the action-reaction story doesn't apply here. Okay, so these should not be, although despite appearances, F2 equal to minus F1, this should not be thought of as an action-reaction pair, because action-reaction law doesn't apply to field forces. It only applies to contact forces, while the forces are being applied to are contact forces. When two objects, for example, if there's a collision, at the point of collision, the forces exchange is an action-reaction pair, because that's a contact force with zero separation. Okay. So I think I've made. So let's moving on. So lambda e, this proportionality constant, this time depends on the system of units. In particular, whether you want to choose units in which the electric charge has separate units from Newton and meter square or not. If it was up to me, I would have chosen this to be 1 and just had the unit of charge in terms of Newton and meter square, or square root of that. So that is called the Gaussian units, in which lambda is taken to be 1, and you don't invent separate units for charge. However, the norm or the convention in most of the books is to use some pretty ridiculous units known as SI units, in which this is not 1, but this is some strange number. And this is because we invented a special unit for electrical charge, which was completely unnecessary. This unit of charge is called Coulomb, most of you know. And in terms of this, this lambda is 9 times 10 to the 9. Sometimes in books it is also written in this form, even more weirder form, which is 1 over 4 pi epsilon naught. And this epsilon naught is sometimes called the permittivity of vacuum. No one really knows what that means, because vacuum is supposed to be empty and propertyless without any properties. Then it doesn't matter, it doesn't mean much to define some property of a vacuum. And this 4 pi is an artifact as most of you can guess, it's the area of a unit sphere that has to do with 3 dimensions. Okay, I'm sorry. So let me make a few comments about the nature of electric charge. What you're familiar with from high school is that electrical charge is conserved. So amount of charge before and after some process remain the same. It is conserved, which, as we have seen in our way of doing stuff, the way we have set up, that means electrical charge density and electrical current density vector, charge density and current density vector will obey an equation which is known as continuity equation, which is just an expression for the conservation of charge, that there cannot be any sinks or sources from which charges disappear, and this led to the continuity equation. So you can ask, what is the origin of conservation of charge, or why is electrical charge conserved? It turns out it is related to some deep result in physics, deep fact of nature, which goes by the name of Noether's theorem, after the German mathematician M.A. Noether. What she showed in the early 1900s is that we have conserved quantities in nature because of some symmetries of nature. So she made this brilliant connection between symmetries and conserved quantities. I can give you some examples. For example, if you have energy conservation, the first thing when someone talks about conserved quantities, the first thing probably most of you think about is energy. And energy is conserved because of a particular symmetry of nature, which is known as time translation symmetry, which means basically if you, let's say you're doing some activity, let's say you're cooking some dish. If you cook something at 9 o'clock in the morning, and if you cook something at 9 p.m., that is 9 o'clock in the evening, the result will be the same. If your procedure is exactly the same, the steps are same, it will give you the same. So there is no special privileged point in time in which you can do and the experiment will reveal a different. For example, if you measure the acceleration due to gravity, if you do some experiment like, of course you cannot do experiments based on sunlight because that will be different. But in general, mechanical experiments, you can show that they do not depend on the time at which you perform the experiment. So this is called time translation symmetry, the fact that there is no special origin of time, a special moment in time that gives rise to a certain conserved quantity known as energy. And then there is a linear momentum, which is also conserved, which you have read in high school. Conservation of linear momentum is related to another translation symmetry, this time is of space. The fact that you cannot have any special point in space. All points are basically identical because, for example, take the Euclidean space, which is what we believe to a great extent our space is. Euclidean space, there is no special preferred origin, right? You can take your original coordinate system to be anything. So the fact that the space, you can set up an origin at any point and get the same result of experiment tells you that our space has spatial translation symmetry, and space translation leads to the conservation of linear momentum. And there is rotational invariance, which has to do with the directions, all directions being identical. Again, you can conduct experiments with your apparatus oriented in different directions, and mechanical experiments seem to give the same answer. So in those cases where you have rotational invariance or direction invariance, that leads to a conserved quantity which is known as angular momentum. So this is a very important result in physics, which goes by the name of Noether's theorem. Not many people are aware of this, but it's a very fundamental, deep theorem which tells you the reason we have conserved quantities is because we have symmetries. Okay, so electrical charge, the conservation of electrical charge is no exception. It is also a consequence of a symmetry of nature, and that symmetry is not a space-time symmetry. It's not spatial translation or time translation or spatial rotation, anything like that. However, it's a completely new symmetry which it takes place in internal space and not in space-time. It has to do with something which has a very name which is not going to be clear to you, but I'll say it because awareness is important. It is due to something which is known as U1 global symmetry. Okay, if somebody is taking an advanced upper division course in electrodynamics, he or she will learn about this U1 symmetry, and that leads to the existence of conserved charges. So it is not a fluke that we have conserved charges. There is a deep reason why we have that. The second property, which most of you are familiar with, that is discreteness, which basically is the idea that charges appear only in multiples of the electronic charge. This was famously established by Millikan's oil drop experiment. Most of you, I guess, have read some version of this in high school. As far as I remember, when I was myself a high school student, at least in CBSE, we had to learn about this experiment and then not perform it in the lab. So it's kind of ridiculous. Anyway, the bottom line is that if you take any object, it can be an elementary particle like proton or deuterium nucleus or whatever, and you can show that the charge of that is some integral multiple of the electronic charge. By electronic charge, I actually mean just the magnitude, not the fact electron is a negatively charged particle, so you should put a minus sign by convention, but I'm not going to do that. So whenever I write little e, what I actually mean is the magnitude of the charge. That is what people call the electronic charge. Okay. So this experiment, I don't know how many of you have actually done it. I did it when I was an MSc student in IIT Kanpur. It's an extremely messy experiment, and none of my batchmates, neither myself, we could get this. Usually what you get is that the droplets are so large. This n is so large that it's a continuum. You get any value from 0 to infinity, and it's very hard to make sense of this. And Millikan did his experiment maybe 100 years back. I don't know how he managed to do it. But what I heard, the anecdote is that Millikan somehow actually already knew the result he was trying to get, and he had a huge amount of selection bias, which is to say that he would arbitrarily throw out data points which would not conform to whatever he wanted, and he kept only a subset of the data which fitted and gave this nice result. So Millikan basically fudged it. Maybe he had some inputs from J.J. Thomson or some other physicists who were working on cathode ray experiments to get some kind of an idea about what this E is. So you might ask, why is it that the proton and the electron, they have the same amount of charge and any other particle? Why is it always integral multiple of the electronic charge? And this you actually cannot explain from classical mechanics, unlike this theorem which applies to classical systems. This has to do with quantum mechanics and the existence of magnetic monopoles. Now, had these magnetic monopoles, if they don't exist, we do not have a charge quantization. But Dirac figured out in the 1930s, so it's a while back, almost 90 years back, that if you have quantum mechanics and if you assume the existence of magnetic monopoles, that naturally leads to an equation like this, where G is the magnetic monopole sitting somewhere in space, and then the Q, charge of a particle, becomes the integral multiple of twice pi over G, which is regarded as the fundamental electronic charge, or the fundamental unit of charge. So this follows from Dirac quantization condition, which, as I said, has been written down in the 1930s, and that leads to the some understanding of why charges appear to be integral multiples or quantized. So most of you can guess that any quantization condition ultimately has to do with quantum mechanics, but the additional twist is that you also need the existence of magnetic monopoles. There's no other way you can explain why else electrical charge will come in integral multiples of some fundamental unit. Okay, so that's a brief comment which I wanted to make about conservation and discreteness, which are the properties of the electric charge. Now let's do something a bit more vanilla, something which you have already learned in high school, which is the electric field strength. I consider a situation in which we have a region of space. We have a bunch of charges, Q1, Q2, Q3, up to Qn, and each of these are located at position vectors x1 vector x1 prime, x2 prime, up to xn prime, the nth charge. And we want to see the combined effect of these electric force of all these on this charge Q, indicated by the blue position vector x. Okay. So we already know Coulomb law tells you what is the force on Q due to Qn, Q1, Q2, and we just have to, force is a vector quantity, so we have to sum all those Coulomb laws, Coulomb forces between Coulomb forces acting on Q due to the other charges. This is exactly represented by this vector sum. So this individual element of the sum is the force on Q due to the ith charge, right? It depends on, as I said, it is x minus xi prime divided by mod of that cubed. Lambda is, of course, the proportionality constant. So I'm talking about the general units now. And then the sum tells you this is a vector sum. Now, if instead of this q you had a different charge q prime, so you might want to know what was the, so at each point, if you can, so for a region containing charges, at each point, if you put a point charge, that charge will experience some force due to all of these, right? So a general thing to define is something which is known as the electric field strength, which is given at any location, and not necessarily occupied by some charge or not. I'm sorry, what am I doing? So let's say any arbitrary location x, and we want to know if a hypothetical charge was to be put here, what would be the force experienced by all of that, right? So that quantity, that feature is captured by the notion of electric field strength, which is the electric force experienced per unit point charge, which can be hypothetically located at that location. So we put a charge, point charge with very little amount of charge q, that is called a test charge, at that location, and then we measure the force acted on it by the rest of the charges in the region, and then we divide by q. So it's the force per unit point charge, and that is something which is known as the electric field. So the stronger this is, that means if E is a large number, that means large vector, that means it's the effect of the electrical force felt by any particle will be very large. So we have regions of high electric field and low electric field. So given this definition, this equation, we can easily divide by q and define what this quantity is. So this is it's the same as the right hand side here, except that we don't have the q because we divided it. So this is the electric field to be experienced per unit point charge for any hypothetical charge particle will be inserted at x. So so this quantity we can define at all points in space. So it's as I have said in the class, this is a vector field, because at each point on space, you can have a small electric vector, field vector, which is given by this equation at each point. So E is a vector field. So at each point there is a small vector sitting here, giving the electric field. Now, one way to depict this situation is through something which is known as electric field lines, which are actually curves, one-dimensional curves, and the tangent to which gives the electric field direction. So given electric vector, we can join them in a way so that the tangent of which at a given location gives you the electric field. And then the density of lines, the density of field lines in a given region sort of measure the electric field, how strong the electric field is at that point. So let me give some examples. This is something which I just ripped off from the internet, supposedly from some exam. So I like this because it has many examples. That's the only reason I ripped it off from the internet. So you have here, for example, a positive charge. Now, a positive charge at any point, the electric field, if you put another second charge, positive charge here, so let's say unit point charge, it will get repelled by it. That's why the arrows are away from it, and they're radially outward. Similarly, for negative charge, they're inward, because if you put a unit point charge, then it will be attracted to it, and the force per unit point charge is what we call the electric field. So these are for the positive and negative charges. As you can see, the tangent at each point gives you the direction of the electric field, which electric field is just the electric force per unit point charge. And then if you imagine if you look at the density, of course this is a two-dimensional or it's a projection. This situation should be three-dimensional, but we can only draw the xy plane on a piece of paper. So if you compute the density of charges, that is, imagine a sphere surrounding A. If you imagine the sphere, the closer the sphere is to the A, the density of these lines become closer and closer. Of course, as you move the part away from A, if you enlarge a circle, then the density of the electric field lines which are threading the surface will reduce. So that means, this is what we mean by the electric field away from the charge is weaker, because the lines now becomes less and less dense. Same is true about this. This third example, what you can see is that this must be a positive charge, because things are being repelled away from this. If you put a charge here, it is being repelled, so positive charge is repelled, so this must be a positive charge. And here D must be a positive charge, negative charge, because things are being attracted to it. So the tangent at each point gives you the electric field and the density of charges. For example, if you make an imaginary circle around here, the number of electric charge lines coming here is very large compared to, let's say, a circle like this, where they are kind of widely spaced and the density is low. So this is a lower field region. There's some more example. I think in this problem you had to figure out what is the nature of the charge. For example, it is very clear E, everything is converging. So simple way to remember if it's positive or negative charges. Positive charges always have lines of forces originating from them, but the field lines for negative charges, field lines converge on them. So they end up. Field lines originate from positive charges and end up in negative charges. So here it's very clear, field lines originating from positive charges and ending up in negative charges. Same is true for here. Most of you are familiar with this from high school. Here all three, none of them are negative, because the field lines are not terminating on them. Field lines are always originating from them, so all of these are positive charges. Okay. As I said, the electric field measures the point on a unit point charge. So the force on a charge of magnitude Q, or charge Q, will be given by the electric field per unit point charge times the charge. So that is Q times E. Continuous volume distribution of charges. Now, we were discussing so far was discrete number of charges, but when you have a lot of charges, typically we have 10 to the 23 charges per unit mole or something like that. So when you have a lot of charges, this sum is difficult to perform, in the sense it is not economic to define such an expression. Then we go to a continuum description in which we replace this sum by an integral, and this charge located at the ith location as some kind of charge density. So we define a charge density, and then charge density by some small volume around this Qn is supposed to give you the amount of charge which is concentrated in this particular point, a small elementary volume around the xn location, right? So the continuum version, the sum will get replaced by an integral, and this qi will get replaced by the density times some elementary volume. So this is what I've done. Density times elementary volume, and the sum gets replaced by all locations x prime. So x prime is the location of charges which is exerting a force at something which is located at x. So x is the field point and x prime is the source point, okay, source on the field. So the electric field at location x, vector x, is given by the electric field due to charges located at x prime, and then you integrate over all charges, all locations. Now the first thing we learn is something which is known as the Gauss law, as promised. And Gauss law is the fact that if you have an electric field, the same information about a vector is contained in the divergence and curl. So let's find out the divergence. So we take divergence of both sides of this equation 1. And if you take divergence of both sides, what you'll get is, if you take divergence of then the divergence is it's not primed. So divergence of E, so it is unprimed coordinate with respect to so it will only hit objects which have unprimed coordinate, like this x minus x prime divided by magnitude of x minus x prime cubed. So we have to take divergence of this, but we've already done an exercise in the last few classes that this quantity is nothing but the Dirac delta function, 4 pi times the Dirac delta function. You should also look up the homework, in which the one homework is also given on this. So this should be very clear to all of you guys now. So this divergence of this quantity is the 4 pi times Dirac delta. And then we also know that if you have Dirac delta function and have something else and you integrate, the Dirac delta, all it does, it replaces by the prime coordinate by the x coordinate. So rho x prime will become rho of x. And this lambda e as it is, and this 4 pi comes from the Dirac delta coefficient. So we have a fundamental equation. Dirac delta divergence of E is 4 pi rho at the same point. So divergence of E at x, I forgot to put an x here. Divergence of an electric field at a particular location is given as proportional to the charge density at that same location. So now we will go to ugly SI units, in which this 4 pi epsilon quantity is given a name, is written as 1 over epsilon naught, where epsilon naught is something which is called the permittivity of vacuum. Then this equation, if we replace by 1 over epsilon naught, becomes rho over epsilon naught. So this is the first Maxwell equation, in fact the differential version. In high school you have learned the integral version equation. Integral version is obtained when you take volume integral of both sides and use Gauss theorem to convert this into a surface integral. There you have the surface flux of electric field is equal to total charge contained divided by epsilon naught. This is, I believe, what you learned in high school. But since you've already learned it, I won't be repeating it here. The more important version is the differential version in terms of the del operator. So the first Maxwell equation tells you the divergence of the electric field. So as you can probably guess, all the Maxwell equations are about divergence and curl of electric and magnetic field. That's why you have 4 Maxwell equations. One equation each for the divergence of E and B, and another pair of equations for curl of E and curl of B. So all in all, 4 equations. In electrostatics, this is the equation we obtain. And it turned out this equation is not just true for electrostatics, but electrodynamics in general. When charges are moving with arbitrary velocities or acceleration, and there's no restriction on the validity of this first Maxwell equation. However, the curl equation we will see is strictly valid for electrostatics, and in dynamical situations that will have a different form. So let's compute the curl. We've already computed the divergence. Let's compute the curl of this expression. Again, curl of E, curl will again hit this guy because this doesn't depend on x, this is an x prime. Now curl of this quantity is 0 actually. So the right hand side gets 0 and we have curl of E vanishing. Again, something we should check. You already know how to use the Einstein summation convention to write down the expression for curl. and you should show that this should be equal to 0. So the integral version of this we will discuss a little bit, again something which you will learn in high school. Now you can apply this over any open surface, and you can take the surface integral n dot this quantity on open surface. The right hand side remains 0. So we will use Stokes' theorem to convert this normal n dot curl of this open surface to a line integral on the boundary of that surface. But this will be true for any general anything. Let's say you have E dot dl, which is the line integral of the electric field along any closed loop. This by Stokes' theorem is the curl of E on the surface, which is surface for which C is the boundary, and that is 0. So we have line integral of electric field around any closed loop is 0. Right? So this is something which you have learned in high school as well. The integral version of both Maxwell equations. One of them is that the Gauss law, which is flux of E on every closed surface, is equal to the charge enclosed by the surface divided by epsilon naught, and the other is that line integral of electric field along any closed loop C is 0. Now this is only true if, most of you know, if the integral of some quantity in which the limits of integration is same as 0, then that quantity must be a total derivative. So it tells you, this is just a basic statement that curl of curl of something vanishes, that quantity must be gradient of a scalar, right? Curl of a vector vanishes. So this you can also glean from this equation. If this is a closed loop, that is the initial and final point is same, and this, if this integral vanishes, then it must be that this is equal to total derivative. Then when you integrate, the total derivative will give you some value of the integral, so value of the integrated thing at the initial and final point, because will be the same because it's a loop. So this will be 0. Okay, so this identically means that there exists something which is known as the scalar potential, such that the electric field is given by the gradient of the scalar potential. So this equation can be solved. This is a differential equation, right? For a solid differential equation, you can integrate both sides and obtain a solution for what phi is. We have already seen the expression for E. So if you're interested in the expression for E for phi, all you do is integrate this. This minus sign comes here, and actually what you should have phi x minus phi naught x naught. But I'm taking x naught to be a point so that I assume that phi x naught equal to 0. Remember, phi x this is a differential equation, so I can add any constant to this, and that equation will be equally valid. So phi is ambiguous up to addition of a constant. Let me fix that ambiguity by defining that at some point x naught phi is 0. Okay. So integrating this, we get an expression for the potential. Most of you again are familiar from high school, and this equation is nothing but the amount of work done. Minus E means you're doing work against the electric field in transferring a unit point charge. So Q is the force on a unit point charge. So minus E is the force against electric field in pulling a unit point charge from, or dragging a unit point charge from location x naught to x, something which you're already familiar from high school. And this equation, if you do the integration, we know what E is. Let me just go back. So this is an expression for E, equation 1. And then we also had the discrete version. You can use either of them, either this equation or equation 1, and then you can do the integration, do this line integral, and we should get is that phi is given by q by x minus x naught mod. Or in the continuum case, qi's will be replaced by this elementary volume located at x prime, and then you integrate over all x prime, all location. So this is the familiar result. The inverse electric field is inverse square, so the potential is 1 over x, 1 over the distance of separation between the charges, something which you're already familiar. Again, this ugly factor of 1 over 4 pi epsilon naught will be there. If you're talking general units, you should put a lambda e here. So this is equation 2, because it's again the form we will use this form very often. So you can rewrite so electric potential, the origin of this came from the curl law. You can ask what does the Gauss law mean for the electric potential. So what we will do is, instead of the electric field here, we will substitute minus grad phi, because E is equal to minus grad phi. This equation we will substitute in the Gauss law, and what we obtain is this equation, which is known by a very well-known name, which is known as Poisson equation. Poisson equation tells you the Laplacian of phi is equal to minus charge at the same location x divided by epsilon naught. So this is the main equation which people solve in electrostatics. Whole of electrostatics boils down to solving this equation for a general class of boundary condition. For a given configuration of charges or for a given potential, you have to solve this equation, and then you know the electric potential everywhere, and from there you can figure out by taking gradient the electric field everywhere. Okay, so Poisson equation is very important. Solving Poisson equation becomes the main thing to do in electrostatics. Now you can consider situations in which you have a bunch of point charges and you're calculating an electric field far from those point charges. Because you're outside those charges, rho at the location where you're finding out the field will be governed by this equation. Rho is 0. There's no charge density because outside sources. For example, it could be if you have a charged sphere and you want to find out the electric potential at some point, some distance s from the sphere, that potential at that region will be given by another useful equation, which is a special case of Poisson equation, which is known as the Laplace equation. Now, both of these are Frenchmen. At that time, during that time, the Frenchmen had huge contributions in almost all branches of physics, mathematics, engineering, and many of their names are engraved on the Eiffel Tower, including the names of these two gentlemen, Poisson and Laplace, along with Lagrange and many other people. So one important fact from this Laplace equation that is outside sources is that electrostatic potential, this phi, the electrostatic potential, cannot have an extremum in a charge-free region. So in a charge-free region, we have Laplace equation holding, which is this 0. Now here, the potential cannot have a maxima or minima. Most of you know from high school that, especially in statics, that particles will settle down at a point or can get at equilibrium at a point where the potential is minimum, right? Now this equation tells you that there cannot be any local minimum or maximum, and most of you can guess why. I guess that the second derivative vanishing. So usually for a minimum the second derivative must be positive, so it cannot be. So I've taken a one hypothetical situation that actually the sign could be reversed. Suppose this is positive, so then in the second derivative in the x direction and second derivative in the y direction is positive. So it's a maxima in x and y direction. This equation 0 means the sum of the second derivatives will vanish, but these two are, if these two are negative, then the third one has to be positive. So then, yeah, for minima these are negative. I'm sorry, what am I saying? So minima, second derivative is negative, and then the third one has to be positive. So it is not a minima in the z direction. So in two directions it will be negative, and the third direction it will be now I'm confusing myself. But either way, the bottom line is that because the sum of them zeros, if a couple of them are positive, the third other one has to have an opposite sign. So in that direction, you will have the opposite behavior. If some couple of them are maxima, this will be a minima. If two of them are minima, the third one has to be maxima. So such kind of points where you have minima in some direction and maxima in some other direction is called a saddle point. Most of you can guess why, because it looks like a horse's saddle. It's bent like this in one direction. In the orthogonal direction, it's bent. One direction is convex, and the orthogonal direction it is concave. That looks like a horse's saddle. So that is called a saddle point. So a saddle point is neither a maxima nor a minima. And then this also leads to another important result, the fact that there cannot be any local maxima or minima in a charge-free region. So where the maxima ends up is exactly at the location of the charges. So the minima, the charge will keep on moving till it reaches the negative charge, or if it's a negative charge, it will keep moving till it reaches the positive charge. Okay. So this behavior is sort of encapsulated on something which is known as an important result in electrostatics, which is known as Earnshaw's theorem, which says that a system of point-like charges cannot be in a stable static equilibrium under the influence of purely electrical forces. The reason, as I said, is because there is no minima The electrical point charge will settle down at a minima, but if there are no minima, it will not settle down ever, it will keep moving. So you can a system of point charges on electric forces on their own, it will never reach a stable static equilibrium. It will always keep on moving or evolving. Okay, this is a physical fact which follows from the math of the Laplace equation. Basically, this is the proof of it. I mean, it doesn't need a huge amount of it. The another important theorem, which is known as mean value theorem, which is again based on some property of the Laplace equation. The fact that it doesn't have a maxima or minima, but all the maxima and minima are located at the boundary of this region, or where the charges are located. That means in the middle, it will be some average of whatever is there on the boundary. So this is an important property. If S is the surface of a sphere, let's say you're in a charge-free region like this, and you imagine a sphere on the charge-free region, a sphere of surface S. Then you can show the average electric potential over the surface of the sphere is equal to the potential at the center of the sphere. So you have a sphere surface, two-dimensional surface sphere, and then if you compute the average electrical potential over the surface, it will coincide with the point at the center of the surface. Okay, so this is something which is known as the mean value theorem, and this is very important because this is one trick to solve the Laplace equation numerically. What we do is we divide all space-time into a grid, and then we give some values, some boundary condition given on the surface or the boundary of the grid, and then the points in the internal lattices or lattice points or the internal locations of the grid, we put some value which is average of the location surrounding it. And this will of course not be exactly accurate, and you have to do this procedure iteratively till the grid settles down to its actual value. The potential at location on the grid settles down to its actual value. So this mean value theorem is an important result on which many numerical approaches to solving the Laplace equation are based. That's why I highlighted it. So this is the average. So phi at any point on the sphere, that is the total phi integral over the sphere divided by the area of the sphere gives you the average, and that is equal to, this is the definition of the average. So we require some boundary conditions for solving the Poisson equation on the Laplace equation. The reason is these are all second order partial differential equations. So the solutions can be given by two particular kind of boundary conditions. So you might think that, okay, I don't need boundary condition because the solution is already known. If you give me charge everywhere, I can find out using this formula, this integral, or this sum, I can find out the potential. However, in most cases in real life, we do not know first of all, in most cases in life, we are solving on a finite region. So we have no idea about charges all over space, right? We only work in a small room in some lab. You have and charges are everywhere. So we do not know. We are solving for Laplace equation in some finite region, bounded finite region. And let's say we also don't know the charges. Usually we have a power supply which only determines the voltage, or the voltage is same. It will turn out to be the scalar potential. So you only know the voltages and the currents, and you don't really know the charges. So if you give me a distribution of potential, how can I determine the potential everywhere inside this bounded region? And it can be done by solving a Laplace equation subject to either of these two boundary conditions. First is known as the Dirichlet boundary conditions, which is to say, given your finite region, specify the potential on the boundary of that region. Okay, at all points on the boundary, specify your potential. If you do that, then this solution to this equation is determined. In fact, determined uniquely. And the other is Neumann boundary condition, which tells you don't need to give me the potential on the boundary, but if you give me the normal derivative of the potential on each point on the boundary, then of course that is enough. So, but the normal derivative of the potential, potential derivative of potential is related to the electric field. So normal derivative means actually the normal component of the electric field, right? So you can think of del phi del n as n dot del phi, but del phi is minus e, so n dot e, n hat dot e. Okay, so if you give the normal component of the electric field on the boundary, that determines the solution to the Laplace equation uniquely as well. So the fact that these equations, these data, either the potential on the boundary or the normal derivative, determines the solution of Poisson or Laplace equation in some finite bounded region of space, is encapsulated in a result which is known as the uniqueness theorem, which can be easily proved using Gauss divergence theorem, or a version of Gauss divergence theorem which is known as Green's theorem. So let's say we have a given region of space in which we have charges given. So if phi1 and phi2 are solutions of Poisson equation with the same charge density and the same boundary conditions. Remember, we're not giving charge density everywhere. We are giving charge density inside a given finite region, and instead of giving charges outside that region, we are only giving you boundary values of potential or normal derivative. So if the given finite region, if the charge density inside that region is given to you, and any of these two data is on the boundary is given to you, uniqueness theorem tells you then the solution to that is unique. As I said, they can at most differ by an additive constant. In case of first case, it is not even there. For Neumann conditions, you only have an additive constant, but for Dirichlet boundary conditions, the solution, there cannot be two solutions to the Laplace equation. There is only one solution. Not only does the solution exist, but the solution under this condition will be unique. Solution under this will be, at most, they will differ by an additive constant, but then we can throw away this piece whenever we want. Okay, so this is where we will end electrostatics. For the general theory, we will not talk about any further about how to solve the equation. All we have shown is that the solution exists and the solution is unique. However, how to obtain the solutions is another story completely, and we will not address that anymore. Okay. Okay, as I said, next thing to cover is when you have, right now we didn't have matter, we had just free charges moving around in space or in empty space. Let's bring in matter. Before we bring in matter, we have to, as I said, consider the field and potential for an electric dipole. So what is an electric dipole? Most of you encountered this object in high school. An electric dipole is made up of 2 point charges plus q and minus q, so equal and opposite, and are placed at close by location x plus and x minus. So this is the normal electric dipole. However, we will be interested in something which is known as an ideal dipole or a point dipole, in which you bring these charges together, that is x plus and x minus, this difference in location, magnitude of this goes to 0. At the same time, you increase the charges, magnitude of the charges q to infinity, so that their product is held fixed or finite. So that product is sometimes known as the dipole moment, P, magnitude of the dipole moment. And in general, you can define an electric dipole moment, which is this q multiplied by the vector from the negative charge to the positive charge, right? So it is directed from negative to positive charge. This is the tail of the vector and the head of the vector. So that quantity will remain finite in this limit. Okay, it will be, of course, this is P is 0 everywhere except at the location of the dipole, and the location we will take conveniently to be the mean value in the ideal point limit. In the point limit, when it's a point object, these two will be thought to be located at the mean value x plus x minus by 2. Now we can find out by using superposition what is the potential at any point x due to an ideal dipole. We will start with an finite or not an ideal dipole, but a general electric dipole, and we will take this dipole limit in which we send the plus to minus at the same time, sending q to infinity. So this is the superposition principle, potential due to the plus, potential due to the minus, and then the sum we Taylor expand, and the one which survived this limit is, so you have to Taylor expand each of the this around x plus minus x minus, so right. So this Taylor expansion you should do on your own. By now you know how to do a three-dimensional Taylor expansion. So this function is a function of three variables, x1, x2, x3, or xyz. So you should do a Taylor expansion in x, y, and z, and then you show the result is something like this. So already we see in the limit, in this limit only one term will survive, which is proportional to the dipole moment, times x minus x prime, where x prime is the location of the dipole, which is given by this halfway point between the plus and minus charge. Okay, so immediately you observe that this is the inverse square law, because there is x and there is x cubed. Mod of x is cubed here in the denominator, so the dipole potential actually is an inverse square potential, not an inverse cube potential, inverse 1 over x potential, which is there for a monopole or a single charge. This pattern will turn out to be something which is true in general. You can have two point dipoles, which are, a dipole is given by an arrow from the negative to positive charge. Now you can have two such dipoles which are oppositely oriented. Right, one dipole is facing up, the other dipole is pointing down, and you can think of a limit in which the dipole moments are p's are infinite, but the separation between the two dipoles are made to approach zero. That object, the coincident limit of two oppositely aligned dipoles is called a quadrupole, and if you compute the potential of the quadrupole, it will turn out to be an inverse third power. Okay, inverse third power. So it will be this divided by 4. So that's third power. So in general, it turns out that this is something which is known as the multipole expansion, which we will not cover in this course. But higher order moments will have lower, electric potential will fall off faster. It will decay faster. So, and you can understand too, in some extent, why this happens. This happens because if there was no point charge, the field will sense the point. At far away, you can sense the point charge, but the total charge of the assembly is 0. So where from very far, you should see a very weak field. So that's why the potential falls off faster. Okay. So this, again, using vector identities, we can write x over mod x cubed, we can write as gradient of 1 over x. This most of you know. Or minus of gradient of 1 over x. So now another way of writing this is that this is an even function of x and x prime. So the derivative of that is an odd function of x and x prime, right? So I can take this minus and grad and replace it by the grad prime, that is the gradient with respect to the prime coordinate. Because it's an odd function, it will be a minus of that. So this is an even function, and derivative of an even function is an odd function, right? So that's why I'm replacing the minus gradient by the gradient with respect to the prime coordinate. Okay, so remember, what is the prime coordinate? Prime coordinate is the location of the point dipole, and x, the unprimed coordinate, is the field, the point at which we are measuring the electric potential due to this dipole at x prime. So the field at x prime due to a dipole located field at x due to a dipole located at x prime is given by this expression, where p is the dipole moment of the dipole which is located at x prime. So this formula will be very important when we discuss dielectrics and electrostatics inside matter. So please, I would highlight this formula, that phi of x is this ugly constant times p dipole moment dot the gradient of 1 over x minus x prime, where x prime, where the gradient is with respect to the location point of the dipole, not with respect to the field point. Okay, what about the electric field? Electric field can be, once you know the potential, by definition the electric field is given by minus gradient of phi, and I will not write this expression because it's a lengthy expression, but it is very simple. You just have to take a gradient of this expression, and I will implore most of you that you work it out on your own. You know if I'm given a scalar, how to find out the gradient. You can find out the components by using the definition of the gradient. You know already the Einstein convention and index notation. From that, please compute the gradient of this expression. Okay, so now let's look at electric. Now that we have set the ground for the matter, because we've already discussed the dipole, as I said, the highlighting formula is this, that the potential is given by this equation. Now we are ready to tackle electric fields in matter. As I said, electric fields come in two categories. Either they're made up of non-neutral object, that is molecules in which or atoms in which the electrons have been stripped off, and the electrons are moving on their own, which are called free charges, or there can be dielectrics or bound charges, okay, in which the electric fields, no matter how strong, they're unable to strip the electrons from the molecules, and the molecules remain, the constituents remain neutral particles, but they do get stretched in the sense that the center of positive charges and center of negative charges separate, and they develop a dipole moment. So induces polarization. Effect of electric fields on dielectrics is that it induces polarization in the dielectrics. The constituents, which are molecules, acquire a dipole moment. So this big P, remember little p is the electric dipole moment of a single point dipole, but there are many molecules, so we will go to a continuum descriptions in which we have a density of dipole moment. So this big P is the density of dipole moment density. And so elementary dipole will be given by this P multiplied by a elementary area d cube of x. That will give you the little p dipole moment in that of that infinite or elementary volume. So this, of course, the stronger the field, the stronger the polarization. So P is a function of E. And later we will consider weak fields in which this P will be linear to as a linear. So this is an analytic function of E, and you can expand an analytic function in Taylor expansion in a Taylor series. It will turn out for weak fields only the linear term will be important, which we will discuss as a case which is known as linear dielectrics. But for the time being, we will keep this general. So P occurs as a result of application of E, so it's a function of E. Now the potential produced by this chunk of dielectric is given by this formula. Right, the potential for a single dipole, we know potential for a single dipole is the dipole moment times dotted with the gradient times this, where x prime is the location of the dipole, and then we sum over all the entire medium, because the entire medium is has dipole moment. So at all locations you have dipole sitting there. So we have integrated over all the entire matter. Okay, then we do some manipulations for this to look a bit nicer. What we will do is do integration by parts. So it is something times function derivative of something else. So we will take this derivative out, make it into total derivative minus. So we will do integration by parts. So when you do integration by parts, this comes, we get two terms. One with this del, the derivative will act on the full thing, and then the other in which the derivative will act on P. So these are the two terms. One, as I said, the first term is the divergence of the whole thing, P times this, minus when the term where the divergence goes to this one. So this, so if you, now this term, so you have two terms. This term is the total derivative or divergence of a vector and in the volume integral. So most of you know now what Gauss theorem tells you. When you have a divergence over integrated over a volume, divergence of a quantity integrated over a volume, and that is equal to the surface integral of the same quantity over the surface. So this is n instead of this will become d2 ds, the two-dimensional area, which is the boundary of this volume, and the del should be replaced by the n hat, the unit vector, and then this vector will remain as it is. So this is, why did we do this manipulation, integration by parts? Because more than this form is intuitively more clear to us what this is. If you look directly and you compare the formula for the potential, somewhere here, you see potential is defined by an infinitesimal amount of charge divided by the distance of the field from the charge integrated over all charges, right? So this is exactly what is going on here. We have some potential due to a unit point charge times some charge density, potential due to a unit point charge times small charge density integrated over all the charges, except this is a surface charge because you're integrating over all surface, and this is a volume charge. So it turns out that a dielectric getting polarized is equivalent to if you replace the dipole moments by a volume charge density and a surface charge density. So polarization is equal to an induced volume charge distribution given by rho and a surface charge distribution given by the surface charge density sigma bound equal to P dot n. So there should be a hat here. I forgot to put the hat. But anyway, I think it is clear. And the minus has to be included. So Griffiths give an intuitive example, understanding of why this happened. Please look through those intuitive explanations. This is why Griffiths is good. It has a physical, what I did was just the math part. And if you follow the math, you will eventually end up on the right result. But sometimes it is very good to have some physical insight in which you don't have to do this math and directly get to this situation. So Griffith has a very nice physical way of arriving at the same conclusion, sort of illuminating what the math steps of the mathematics is talking about. So from now on, we will forget about the dipole being polarized, the matter being a polarized dielectric, and we will replace it by a surface and a volume charge distribution given by this, okay, because they're physically identical. Not physically, they, for all intents and purposes, they behave identically. So now, what about Gauss law inside dielectrics? Now, inside dielectrics, we can push in some charge from outside, like you can send a current through, put a wire. For example, you can take a piece of semiconductor and you can connect it to an external circuit in which you drive charges through it. So you can have an external amount of charge being pushed into it. But also because you're subjecting it to an electric field, it will develop polarization, and that is equivalent to some kind of bound charges, right? Density of charges. So at a given volume inside the dielectric, you will have free charge as well as bound charge. The total charge, Gauss law tells you divergence of E is proportional to total charge divided by epsilon naught. This, of course, happens on its own. We don't have to push this charge in. We just subject it to an electric field, and automatically it gets polarized and develops this bound charge. So divergence of E is equal to this sum. But then we just learned that the gradient, the bound charge density, bound charge volume density is given by minus of divergence of P. So we will do that. We will replace this by minus of divergence of P. And so this is divergence of E here and divergence of P here. And we will combine them by taking this rho bound here, which is equal to minus divergence of P. So when you take it here, it will be plus divergence of P. And so we substitute here and bring the term here. What we will get is a new equation, which is, if you multiply both sides by epsilon naught and bring the rho bound here, you get a new equation, which is divergence of D equal to rho of free. And this D is defined to be epsilon E plus P, okay? Epsilon times the electric field time plus the polarization density, polarization dipole moment per unit volume at that location X. So I've suppressed all spatial indices, spatial, every you should imagine a bracket X vector, bracket X vector, bracket X vector. I have not bothered to, because then it gets very cumbersome to carry around. So the idea is that for dielectric, Gauss law, if you want, because rho bound we cannot measure, we will try to eliminate them from all our equations. Free charge is in our control because we are pushing it from inside, outside, and we know we are controlling it. So rho free we know. On the other hand, the bound charges develop due to polarization, and there's no way we can go inside the dielectric and figure out how much bound charge is there in per unit volume. So instead we will use with D, in which case Gauss law will be written in the simple form. Divergence of D is rho free, okay? Now E is unknown, D is also unknown, because D requires two new things, E and P. We cannot also go inside and measure the polarization density inside either. So it seems like there are too many unknowns here right now. So the one way to simplify the situation is through something which is known as the constitutive relation, which tells you, okay, polarization is caused by the electric field, so maybe we know what this function is, and a special class of functions or special class of situations, let's say, in which the electric field is not very strong. In that case, any arbitrary function of E can be expanded in power series, and for weak electric field we can truncate the series at the first term. The second term. The first term is the leading term when E is 0, because E at E equal to 0, no polarization, that term has been set to 0. And then the linear in E term is there. Of course, the quadratic, cubic we have all dropped because E is small, so quadratic and cubic are even smaller. So the second and third order of smallness, and we will drop all of them. So this situation is called linear dielectrics, and the coefficient is this ugly combination epsilon naught chi. Chi is sometimes called the electric susceptibility tensor, and epsilon naught, as I said, is an artifact of choosing ugly units. So it will be there to haunt you in every expression, and of course it's just a burden which you have to carry forward in every equation in SI. So One important thing which I want to point out, it doesn't have to be that P is directly in the direction of E, right? This is the tensor dot product, which means if you write down the index notation, this equation, this is index-free notation, but you can write down the ith component. Because it's a vector quantity, you can write down the ith component of both sides. So ith component of both sides, this is a tensor, so it will be chi ij dotted with E, so there's ej. Again, count the number of free indices on both sides. There's a single free index I here, and j is the dummy index, so it doesn't contribute to the tensor rank. It gets summed over everything. So it's clearly pi, the ith direction dipole component in the ith direction is not proportional to the ith direction electric field. It is proportional to somewhat the j direction or the sum overall j direction. So it is not necessarily true that it is if, for example, it could be that Ej is non-vanishing in the 2 direction, but we will have a non-vanishing P in the 1 direction. So E2, because it has summed over everything, the second electric field or the second direction will contribute. And if it turned out that the only direction in which we have introduced E in 2 direction, that will produce a dipole moment in the 1 direction. So it is not necessarily true that they are along the same direction. This doesn't always happen. In fact, for crystals, it doesn't happen. So this chi is sometimes, as I said, the coefficient is this chi ij is sometimes called the electric susceptibility tensor. And if we feed this in this equation, we will have E, and we can take out everything other than E outside and lump it into a single term, which is known as the relative permittivity tensor. So, sorry, not relative, the permittivity tensor. The permittivity tensor of a linear dielectric is this epsilon naught constant, identity plus chi. Okay, identity plus chi. So one good thing about this is that we know curl of E is 0, right? So we can substitute D is equal to, for linear dielectric, the fact that it is E dot epsilon dot E into this equation in the Gauss law. So we will have del dot E dot E. Okay, so I need to distinguish. One dot product is the vector dot product, and this, I shouldn't have used a center dot for both. In fact, this is a typo here. This should be a bottom, just like here. And the center dot is for, the bottom dot is for a vector dot product, and the center dot is for the tensor product. So if you write this equation with D being equal to this, you can write this equation in index notation, and you will get epsilon ij. So epsilon ij will be the ij component of this equation. Epsilon ij is epsilon naught plus identity ij component is Kronecker delta ij, and chi ij component just chi ij. So you will get the Gauss law in terms of the potential. Doesn't give you a Laplace equation, the Poisson equation, but something close to Poisson equation. Epsilon ij times del I del j phi equals to minus rho of free. Now this equation is again an elliptic second order differential equation, and most of the tricks you can solve Poisson equation can be used to solve this one as well. However, we will deal with a simpler situation in which the chi will be proportional to the delta ij, right? So delta ij meaning all directions are identical, x1, x2, x3, 3 directions are identical. So it is chi ij is proportional to some number times delta ij. So that would mean that epsilon will also be proportional to delta ij, because this is delta ij and now chi is also being made into delta ij. So these two terms are proportional to delta ij, so it will be some number times delta ij. In fact, in this case, this constants epsilon and chi will be related by this, which you probably have read already in high school. This equation will then become the regular Poisson equation. And I'm sorry, the equation got cut off at the denominator, but this side will become epsilon delta ij. You can easily see what happens if you substitute this guy here, epsilon delta ij here, then it becomes this number epsilon times the Laplacian equal to minus rho free, and then that epsilon number you can send it in the denominator, so it will be minus grad square phi or Laplacian phi equal to minus rho free divided by epsilon, not epsilon naught, by epsilon. So let's look at some of the boundary conditions. As I said, for every time we look at this kind of Poisson-like equations, we need to know the associated boundary conditions which will help us solve this equation. So let's look at the boundary conditions which we have the interface between two media. So let's say we have a situation in which have boundaries separating two dielectrics epsilon1 and epsilon2. These two are linear, isotropic dielectric. That's why they can be specified by a single number instead of a whole tensor. So it turns out that Gauss law and the curl law for electric field, the Gauss law for dielectrics, they give some kind of boundary conditions, consistent boundary conditions. And these are, you apply Gauss law, this condition, the rho free, divergence of du is rho free, over a pillbox shaped Gaussian surface which straddles the, you can see the Gaussian surface is a small cylinder. It's a flat cylinder, almost a flat cylinder. The lateral sides of the cylinder is very small compared to the cross-sectional area of the cylinder. So this is called a Gaussian pillbox. It's a pillbox shaped Gaussian surface which straddles, which extends to on both sides of the media, both sides of the boundaries between the two media. And you apply Gauss theorem to such kind of a pillbox shaped surface. Now the surface has three contributions. There is the top surface of the cylinder, there is the bottom surface of the cylinder, the pillbox, and of course the lateral vertical sides, single vertical side of the cylinder. Now we are going to take a limit in which we will make the surface goes to zero as these top and bottom surface approach the boundary of the medium from both sides, up and over and below. In that case, the contribution from the lateral side will vanish, and the complete flux contribution, Gauss law divergence theorem applied to this, will get contribution from the over and under, this top surface and the bottom surface. And you can imagine if I take a volume integral over the pillbox, the volume integral due to Gauss theorem will get turned into a flux integral over the top surface and the bottom surface. And the volume integral of the charge free will give you whatever the free charge is on the surface. Right, because the moment we take this volume approaching this surface, the only finite contribution is going to come from the boundary surface. That's why you have a surface charge here. And then the left hand side will be the area times the under and over minus the under, because this minus sign is because the outward normal is pointed for the surface below. The outward normal, this is the normal n at the surface. And at the top surface it will be same as this one, but at the bottom surface it will be the minus of this. So that's why you got a minus sign. So d over minus d under, normal component of the electric displacement across this boundary, the difference or the discontinuity of the normal component is equal to the free charge which is present on the surface. And also the curl theorem, which you can apply curl result, curl of E equal to 0. You can apply this over a rectangular loop, again, which you have a rectangular loop, and you have, which is across the boundary of the two dielectrics, and you have again we will consider a rectangular loop such that this edges of these two vertical edges of the loop approach 0, because we will take this line segments to approach the boundary, and in the limit any contribution from the sides will vanish, provided of course the E remains finite, and we are assuming E is finite. So finite times the vanishing length will give you 0. So then only non-vanishing contribution will come from this one and this one. Because curl of E is 0, that means the E dot dl in a closed loop, E dot dl is 0. So then E dot dl from the upper surface and E dot dl from the lower surface should add up to 0. But then we are going anti-clockwise. So the tangent vector for this lower side, the tangent vector is same as this. But for the upper side, we are going in anti-clockwise direction. So the line element in this upper segment is equal to minus of t. That's why you get a minus here. So you will have E minus over plus E under equals 0, or E over and E under, the parallel component. Line integral always means, as you know, the parallel component to the line segment or the loop element. So that's why the parallel component. We cannot say anything about the normal component of E, but we can definitely say something about the parallel component of E, which is parallel to the boundary. That will be continuous. Okay, E is continuous. The parallel component of the E across the boundary is continuous, and the normal component of D across the boundary is discontinuous, with the discontinuity, with the difference being equal to the surface charge density, free surface charge density. So this is true for general case. There is no approximation, no linear dielectrics, no isotropic, nothing. This is very general. And then for the linear case, we know that D is equal to epsilon times E, and then E equal to minus grad phi. So this is the linear isotropic dielectric condition. If we plug it here, we get a condition for the potential. So potential tells you that the tangential derivative, that is the derivative in this direction. As I said, in vector calculus, multivariable calculus, you have many derivatives. As many directions, there'll be as many derivatives. So the derivative in the tangential direction is continuous as a consequence of this, and the derivative in the normal direction is discontinuous. I just replaced this by epsilon over times partial derivative using this formula. So the potential is discontinuous, and the discontinuity is given by this. So rho f is same as rho free. Sigma f is same as sigma free. Okay. So in terms of potential, if we solve the Poisson equation, we will need to use these boundary conditions for a consistent solution. And again, if you look at Griffiths, there's a whole chapter devoted on how to solve boundary value problems in dielectrics. For example, if you have a dielectric sphere situated inside a dielectric which extends in all directions, so a sphere of dielectric epsilon 2 located inside in the dielectric of epsilon 1, and if there's some charge on the sphere, what is the total electric field produced or the potential produced? Those kind of problems are done using these boundary conditions. Again, as I said, regrettably, we will not have time to cover these, although these are what constitutes the essential, the real part of the study of electrostatics. We will not have time to cover any of that. That requires a course on its own. Then there is electrostatics. The energy contained in electric field. So one word about this before I actually go over is that usually the way the fractal system was imagined is supposed to be a follow-up course where you do the details. But the ridiculousness of the fractal system in IIT Hyderabad is there is no follow-up course on this. So this is going to be your only chance. So most of you who are really curious about learning how to solve Poisson and Laplace equations in a variety of situations should take the physics department course, where you can learn these things from the very beginning again. Maybe a bit more detail, and that I'm not so sure even that is done in a very detailed fashion. But yeah, if there was a 3-credit course, we could have had ample time to cover this. Anyway, let's move on to energy contained in the electric field. Now, you might think that, okay, energy is contained only in the charges, because the charges are the ones which are experiencing forces, and then charges are also attracting other charges, so they are doing all the work. So it must be them which contains the energy, and it turns out to be not true. So let's consider from the beginning premise that the charges do work on each other, and that leads to some kind of potential energy. So a charge which is located at location x, which is given by rho times the infinitesimal volume, density times the infinitesimal volume is the infinitesimal amount of charge. And the potential energy of that charge, as you know, most of you know from high school, is the charge times the potential. And then you integrate over all volumes, that gives you the total potential energy. You will notice that I put a factor of half. And this factor of half, as some of you can guess, is because of double counting. Is to prevent double counting. So when we integrate over all space, what we have is potential energy of each charges, but then potential energy, you should also always think of a pair of charges. You have two locations x and x prime, and the potential energy of that pair of charge is given by rho phi, or rho x prime phi. So we are double counting. Instead of potential energy of a pair, we are counting it twice, one for the first charge and one for the second charge. So this factor of half is inserted in order to get rid of the double counting. If what I'm saying is not, it's too fast and not adequate, please go to Griffiths. There he explains in a nice way why, in a more instructive, a more number of steps, he shows gradually how this half factor comes about. But as I said, it comes about because when we count like this, when you integrate over some overall charges, you're counting pair of charges twice. One first charge and second charge, you are counting it separately. So in effect, you're counting the energy twice. Now at this step, you can do some manipulations. Well, what you can do is to replace rho using Gauss law. So divergence of E is rho by epsilon naught. So you can replace rho by epsilon times divergence of E, right? And then you can do integration by parts and some more manipulations, again, which is all laid out in Griffiths. It turns out that you end up an expression where there is no rho left and only electric field is left, E. So this is a very curious expression. So even for regions outside sources where there are no sources, you have a non-vanishing electric field, and the energy seems to be proportional to the square of the electric field, scalar product of the square of the electric field itself. So even if this region has no charges, we began with an expression which had charge, but that has disappeared due to Maxwell equation. We have been able to convert it into a completely an integral involving E. But E is present even when there are no charges present. For example, the famous example I gave, a region outside an electric point charge doesn't contain any charge, but there is a non-vanishing Coulomb electric field. So that field has some energy. This is given by this expression. And if you remove this volume element, then it gives you the energy per unit volume. That is the energy density in electric field. It turns out that the energy density in electric field is given by this expression, half epsilon naught times E square. Again, the epsilon naught we have to carry around every time because you're using ridiculous units. For Gaussian units, you can replace the epsilon naught by 1 over 4 pi, so it will be 1 over 8 pi E square by E square. Okay, so the little u means energy density, big U means total energy, okay? So electric field per unit volume contains this amount of energy. So it's a physical object. And then inside dielectrics, you can repeat the same. You can ask what is the energy stored inside dielectrics. Now inside dielectrics, there are free charges and bound charges. So you might think like, okay, instead of rho, I will add rho free plus rho bound. But at the same time, you remember where this expression comes in. This expression comes because the way we set up this calculation is because we count the charge times potential. It is the potential in which it is the amount of work done in bringing this charge to its position from infinity, right? But the bound charges we don't really bring in from infinity. It's only the free charge which we push into the dielectric are some things which we do, the external agency, for example, us, we are doing to put this amount of free charge inside. So we are moving only these, and the entire work done should be made up of free charges. There is an associated energy, of course, work done, which is causing the dipoles, stretching the molecules from neutral, having zero dipole moment, to something non-vanishing. So stretching the dipole moments also will have some work for sure. But anyway, if you charge from this expression, this automatically takes into account everything because the potential knows about the contribution of the stretching dipoles. Okay, so then you can use the Gauss law and write this as divergence of D. Let me think about it. Right, so you can say, okay, start from this naive expression here for the dielectric, which is there. This is the electric field itself, and of course there's a amount of work done due to stretching the dipoles. So that contribution has to come when you stretch a dipole, increase the dipole moment of a point dipole from P to P plus dP. And if you add those expressions, what you get up is here. So you can derive this energy per unit volume of energy of the dipole moment, energy of a dielectric in two ways. One, you can think, okay, one is the energy stored in the electric field plus the amount of work done which to stretch the dipoles. Those two add up. This will give you this expression. Or you can start the fact that, okay, the configuration we created is after moving free charges, and the electric field, the free charges motion is already affected by the bound charges, so we don't need to worry about the bound charges at this point. We are only moving the free charges, and the amount of work done will be given by this expression. And then you use Gauss law to replace rho free by divergence of D, which is going to lead to this expression as well. I'm skipping the steps. You can look up Griffiths. The missing steps are not important. The important thing is to know that it's D dot E, right? So the energy density contained in dielectrics is D dot E, and since D is equal to epsilon naught E plus P, so epsilon naught E times E will give you the energy contained in the electric field, and P dot E, that term is the work done to stretch a dipole when you polarize the dielectric, right? So this contribution gets energy from two ways. One is the field stored in the potential stored in the, energy stored in the electric field itself, and then potential energy you stored when you stretch the dipoles, stretch the molecules into dipoles. So these are important expressions, as I said, but I think this is more important than this one, because it tells you that the empty electric field, where empty of charges, a region which is empty of charges, there are no physical particles there, but the electric field itself can contain some amount of energy which it can transfer to point charges. So it's a physical entity as real as the point charges or the point particles themselves. Okay, I think our discussion on dielectrics is more or less complete. As I said, the bulk of the discussion would have consisted of solving the Poisson equation for dielectrics, but we're not going to do that in this course. So the only thing left today for today's class is conductors. Now, remind yourself that conductors, I've said, they are objects which are a kind of matter which have an infinite supply of free charges, which are formed by ionizing the molecules. The electrons are stripped off, and there are infinite number because 1 mole contains 123. In effect, if you add up the contribution from the whole conductor, it almost has an infinite number of free charges, plus and minus charges, we will assume. Now, what happens when you put this kind of an object inside an electric field? Well, the electric field will enter the conductor, and the moment there is an electric field inside the conductor, the free charges, which are free to move around but not free to move, leave the surface. So it will move around inside the conductor, but it cannot escape the grip of the conductor. It will stop at the boundary. So as you can imagine, there will be no polarization, but plus charges will be repelled by the interior electric field, and the minus charges will be attracted to the electric field. So these kind of plus and minus separation of charges on the two opposite boundaries will keep happening, and because there are infinite number of free charges, this kind of separation or induced charges will continue till the induced field, due to this separation of charges, cancels entirely the applied electric field inside. Okay, so inside the conductor, there is no, after this induced induction of charges, there is no interior electric field. If there is a non-vanishing electric field, then the separation of charges will continue till a point this is neutralized completely. So this is going to be a defining property of conductors in electrostatics, that inside, I emphasize the word electrostatics because when we go to dynamical situations, this will turn out to be not the case. In electrostatics situation, the final configuration is given by the condition that there are no electric field inside the dielectrics. The induced charges cancel the electric field due to the induced charges, separated charges, completely neutralize the applied electric field. So if this is the case, so inside the conductor there is no finite electric field, it vanishes. If this is the case, then the entire conductor should be an equipotential. For example, take 2 points inside the conductor, right, 1 and 2. The difference between their potential is given by, most of you know this formula, we established a few slides earlier, but you also might know from high school. The difference potential is minus E dot dl from 1 to 2. Because E is 0 inside, so this integral vanishes, so we have phi 2 equals phi 1, or phi 2 minus phi 1 equals 0. So for any two arbitrary point inside the conductor, the potential must be the same. The entire conductor is an equipotential region. Okay. Another thing which comes from considering Gauss theorem is the electric field at the boundary. Now, the electric field is entirely normal at the boundary, and the reason for this is again the same thing. Let's say 2 points on the boundary, phi 2 and phi 1 at points on the boundary. Because the conductor is an equipotential surface, this is 0. And E dot dl will be a tangential component because it is along d dotted with dl means the tangential component. So the tangential component is 0. If this is an equipotential surface, then the tangential component has to be 0 along the surface of the conductor. So at the surface of the conductor, there is no tangential component. It can only have a normal component. How much is the normal component? Normal component is given by the induced surface charge on the conductor, or whatever the surface charge density. Sigma is all the symbol for surface charge density, that is the charge per unit area, divided by epsilon naught times the unit vector at the boundary. So it's entirely along the E out, or E at the boundary of the surface of the conductor is entirely along the normal. How do we establish this equation? This is known as Ampere's law. Ampere's law you obtain by again looking at this kind of a Gaussian pillbox, except instead of epsilon 2 you have conductor here and vacuum or some other dielectric vacuum here, for example. So inside there's no electric field, so the contribution from the lower surface would be 0, and outside it is entirely normal, so it will be E times the surface area. There's no upper area of the upper cap, and that is equal to sigma free, whatever is on the boundaries. So divided by epsilon naught, because we are using not exactly this equation, but equation for E. Let me just go back a little bit, or maybe this is also good enough. So epsilon naught E equals to sigma free. From that, from epsilon naught E equals sigma free. D under is 0 because inside the conductor there is no electric field, and hence there is no dielectric displacement field either. But epsilon E equal to sigma free, epsilon naught E. So when you bring down the epsilon, you get this equation, which is Ampere's law. Okay, again, Griffiths also has this nicely described. So at any point on the conductor, the entire electric field, if it's inside, it is 0. If it's on the surface, then the electric field is actually normally directed from the surface, proportional to the normal vector, and the magnitude is given by the charge density at that point. So I forgot again to put the label x, which point, so sigma at x. Now, in high school, you spend a lot of problems in figuring out the capacitance of a conductor. Now, what do you mean by capacitance of a conductor? Well, as I said, the conductor a good conductor is something which has an infinite number of charges. Of course, most of them do not have infinite number of charges. The idea is that, the more the number of charges, the easier is it to it's easier to put the amount of free charges if the potential doesn't increase, if phi doesn't increase when we put a lot of charges in it, and that defines the property which is known as capacitance. So something which is easier to charge will lead to the increase in potential, very little amount of increase. Okay, so then we can push in a lot of charges here with very less increase in the potential. If the potential increases by a lot, then there'll be an electrical short in which the charge will leak out, so it's not a good conductor. So this capacity to hold charge per unit increase in potential is dubbed capacitance. As I said, the better the conductor, the higher this capacity is, and then you solve a particular bunch of problems on this, which I'm not going to do. But yeah, there are a bunch of problems, configurations of various different conductors which have more capacity, and this quantity depends on the geometry and the shape and the topology of the. You can have a bunch of conductors, and the combined capacitance is actually more than individual. So then, and how they are arranged. So this is a very geometric quantity. The answer depends a lot on the geometry. So these kind of problems you've already done in high school, so I'm not going to repeat this. But just a review, this. But Griffiths also has a bunch of problems. You can look at those. So this is the summary slide. What we covered today is static electrostatics, and here are the Maxwell equations which govern everything, every phenomenon in static electricity. So for vacuum, the two Maxwell equations are the Gauss law. This is the differential version, and this is the differential version of the curl law, or the fact that integration of line integral of electric field around a loop is 0. That is same as saying that curl of E is 0. The differential version, the local statement, that is, each of both sides have a location x vector, which I didn't indicate, but this is x. So they're local, but in high school you've learned the integral version. This is the integral version of this Gauss law, is that flux on over a surface, closed surface, is equal to the total charge enclosed divided by epsilon naught, and that E dot dl, closed integral of E dot dl is 0. So again, as I said, that in reality we don't work with the electric field. We, most of the time when we're solving problems, we tend to work with the potential, because it's a scalar object. So the scalar object, this equation implies that E equal to minus grad phi, and then that grad phi we insert here, and then if we do that, you get Gauss law in this form in terms of potential. This equation, as I said, is a very important equation in electrostatic, and people spend a huge amount of time, a century, in the 1800s and 17 and 1800s. People wrote this equation and looked at solutions. This is a Poisson equation. And then for dielectrics, we need to modify things a bit, because in order to include the effect of polarization of dielectrics. The dielectrics, in addition, they develop polarization, and Gauss law is better stated in terms of this equation. Divergence of D equal to rho free. Free charges are the ones we externally push into the dielectric. The curl law remains as it is. There is no difference. These two are the Maxwell equations for arbitrary dielectrics. Now, as I said, these are two different quantities. Here we have the same quantities, so there are too many unknowns. So we cannot solve this unless there is some relation between D and E. And we considered a very special class of dielectrics, which is known as linear dielectrics, in which D is proportional to E and this proportionality constant. In some cases it's a tensor. It's called the permittivity of the medium, or permittivity of the dielectric. I guess most of you are familiar with dielectric constant or relative permittivity, which is the ratio of E to epsilon to epsilon naught. For linear isotropic cases, these three equations can be contained or encapsulated in a single Poisson equation, which is this. So notice the difference is that instead of epsilon naught, you have epsilon here, right? And then I didn't write down the boundary condition, but perhaps you should, a second slide, we should also have had the boundary conditions for the, here, especially here, if you have two dielectrics, what are the boundary conditions? That the fact that the normal derivative, normal component of the D field is discontinuous by an amount which is equal to the surface charge density, surface free charge density. And this equation has the bearing that the tangential component, or the parallel component parallel components, because if you have a two-dimensional surface, there are two tangents. And let's say the surface is the xy plane, then the tangent vectors are the x vector and the y vector. So it will lead to the continuity of the, this is equal to 0 means continuity of the parallel components. Yeah, so this should be a vector equation. This is a scalar equation because there's just one component, so it's italicized is fine, but this one should have been boldface, because the tangent vector, there is one line here, one direction indicated, but there is also the orthogonal direction, which there is another tangent vector. So this is actually a vector in the whole xy plane, or whatever, the surface of the boundary surface parallel to the tangent vector parallel to the boundary surface is a two-dimensional vector. So it should 2D equation should be a vector. Okay, we will stop here, and in the next class hopefully we will begin magnetostatics. Okay, thank you.